Reviewing geometric series. A little bit of background information here. Example 1. Okay. It appears that this geometric series is going to converge because the common ratio is less than 1, it's 1/2. It might be best to generate a few terms. So I did that here. Okay. So we're going to identify the common ratio as 1/2. And because that's less than 1, we know that we can find the sum of all of those terms of that infinite series. And using the formula up above, we need to know what that first term of the series is. That's 3 divided by 1 minus the common ratio, 1/2. Simplifying, we're going to get a sum of 6. Be certain to be careful when you're finding the sum, and what I mean is this: make sure that you know what the first term is. And just because you see 3 here doesn't always necessarily mean that the first term is going to be 3. It depends upon what the index starts with and what the exponent is. Had this exponent not been n minus 1 but just n, okay, then our first term would have been this value right here. So that's why I think it's kind of helpful in some regards to generate a few terms. Right, example 2. Okay, looking at the structure of this expanded series, okay, if we want to identify the common ratio, it's alternating, so that tells us our common ratio is going to be negative, and it's negative 1/2. And the absolute value of that is less than 1, so that indicates to us that this series is going to converge, so it is possible to find the sum. The first term, a sub 1, is 1 minus the negative 1/2. So whenever you're finding the sum, it's important to use the sign of the common ratio. Okay, simplifying, we get a sum of 2/3. As suggested by this series, it appears that the common ratio is going to be a fraction. It's going to be pi on top and 2 on bottom. This common ratio is greater than 1 if you estimate pi to be about 3.14. So this geometric series diverges. It won't have a It won't have a sum. All right, for example number 4, it is multiple choice. All right, studying this concise notation, the summation notation here, it might be helpful to generate a few terms. All right, as suggested by the expansion here of a few terms, okay, it appears to be a geometric series. Common ratio is 1/3, which indicates that it converges, since 1/3 is less than 1. So now we're going to find the sum. Okay, well, the first term right here, and it's kind of strange just the way they have two variables, but if I equals n, then we just start with n first and then add one more. So the first term is going to be 1/3 to the n over 1 minus 1/3 the common ratio. Okay, we're going to clean this up. This will be 2/3 multiplied by the reciprocal, 3/2 times 1/3 raised to the n. And as we start scanning the choices, it appears that that's going to be choice C. All right, next we're going to go to cliff note number 6, the nth term test for divergence. All right, the nth term test for divergence, example 1. Okay, what we do is we find the limit as n goes to infinity. All right, observing that that limit is 2/3. You remember there's a couple ways that you can get that. You can just think of this being a rational function and comparing the exponents and grabbing the coefficients since these exponents are both the same. I think a lot of you guys like the L'Hopital's rule. Find the derivative of the top, the derivative of the bottom, you get 2/3. Okay, because this is not equal to 0, okay, we say that this series will diverge. This is the test for divergence. If we do end up getting 0, then this test is inconclusive. All right. So let's see, example 2. It's almost there for me, so I'm going to leave it there. You guys have it printed there on your paper. So the limit as n goes to infinity. of 3n minus, I think the minus 2 is not part of the exponent. Yeah, 3 to the n. All right, plug in infinity. It's indeterminate. Okay, so then we're going to use L'Hopital's rule. And this allows us an opportunity to revisit the derivatives of exponential functions. The derivative of 3 to the n would be itself times the derivative of the exponent, which is 1, okay, and then times ln, natural log of the base. Okay, and the derivative, of course, of 2 is 0. The denominator will be the same thing. You differentiate. Okay, that will cancel to 1. This is equal to 1, which is not equal to 0. Okay, so this series will diverge. All right, taking a look at example 3. All right, looks like they're trying to be tricky on this one, but just kind of studying it before we jump right into it, we can see that we can simplify cosine of pi over 3. So we'll do that first. The cosine of pi over 3 is a half, so this really reduces to the series a half to the n. Right, and if you think about this, this is a convergent geometric series with a common ratio of a half, but on this particular note card, this page, we're looking at applying the nth term test. So if the nth term test should fail, okay, because we know this is convergent, and the nth term test is only for divergence, but we'll just go ahead and use the nth term test, knowing what the result's going to be. As n goes to infinity, 1/2 to the n here. Okay, you can plug in infinity here. Another way to think about it, to kind of clean this up, is that 1/2 to the n would be 1 to the n over 2 to the n. Okay, plug in infinity here. 1 divided by super large is going to be 0. So because we get 0 in this nth term test, okay, this nth term test fails. It's inconclusive. Okay, but again, like we said, we noticed that that would be a geometric convergent series. All right, example 4. All right, if we're asked to apply the nth term test, then our work would need to be the limit, as you need to write down the limit as n goes to infinity. Otherwise, I think it's pretty apparent that the nth term test is going to be inconclusive here. Right, so it's obvious that this is going to go to 0. If it's not obvious, then you can apply L'Hopital's rule, and you're going to get 1 over 2n minus 9. Plug in the infinity, and you're going to get 0. Okay, so the nth term test is what we would say is inconclusive. All right, let's review the next test, series test, which is the integral test. All right, we're going to use the integral test if our series is a positive, continuous, decreasing series. And you might want to refresh your memory and just kind of scan this information here regarding the integral test. All right, one of the most challenging things, in my opinion, about using the integral test is that we have to state that the function is continuous and positive, and maybe easier said than done, but just observing what the series is, okay, we can just state that. And then the decreasing part, we would have to find the derivative to show that the derivative is less than 0, indicating that the function is decreasing, that all the terms are decreasing. Okay, and again, that's easier said than done. Sometimes finding the derivative is a little challenging. So at this point, I'm just going to avoid all that and say that these problems on this page are going to be able to be solved by the integral test. So we're not going to state that it's continuous positive. I'm not going to find the derivatives of the series to prove that it's decreasing. Okay, we're just going to jump in and act like they are, which they are. Okay, series that we can use the integral test on. All right, we're going to try and determine if this series converges or diverges. We've already determined that it's not geometric. The nth term test isn't going to help us. So we're going to use the integral test because it's positive and decreasing and continuous. So we're going to model this with a function. So lower limit, upper limit. Notice it's an improper integral. We're going to have to write it proper. Replace every n with x. Okay, as I write this down, the thing I'm thinking about is how am I going to integrate this? Does it require integration by parts, or is it just simply a u substitution? And thank goodness it is just a u substitution situation. Okay. So u is the exponent and du is negative 2x dx. Okay, so here's the x part of that derivative. Here's the dx. We just need to bring in a negative 2. So we have a negative 1/2 out front. Okay, and I'm going to do 2 steps over here. I'm going to rewrite it as a proper integral, but I do have the negative 1/2 pulled out in front. So the limit as b goes to infinity, 1 to b. Okay, I'm going to rearrange it, e to the u, okay, and then we're going to have the du here. Okay. I guess I didn't really rearrange it, I just put it in terms of u. Alright, and let's proceed, let's integrate. Antiderivative is e to the u, negative x squared, evaluated from 1 to b. Let's just bring along the negative 1/2 and the limit to the evaluation. So this is e to the negative b squared minus e to the negative 1. Okay, I'm going to do a little cleanup on that. This would be 1 over e to the b squared minus 1 over e. Okay, now let's go ahead and plug in infinity. So I still have the negative 1/2. I'm going to plug in the infinity so the limit drops off. Infinity here makes this super large, so this denominator will be super large. The value of the fraction will go to 0. So 0 minus 1 over e. Okay, it looks like it's going to converge because I'm going to get a numeric answer, not an infinity. So multiplying, it looks like I'm going to have positive 1 over 2e. Okay, so I'm not saying that the sum of the series is 1 over 2e according to this test. It just says that if you have a value here, not infinity, that this series is actually going to converge by the integral test. All right, number 2. Notice that the index starts with 2, and that makes sense because if you were to start with 1, the natural log of 1 would be 0, and that would be undefined. So it makes sense that this integral is going to have a lower limit of 2. Okay, so this series right here is positive, continuous, and decreasing, so I'm just going to jump right into equating it with an integral. So let's consider the integral from 2 to infinity. It's improper. We'll rewrite it proper, of 1 over x ln x with the dx. Okay, so I'm going to rewrite it proper first. Oh, yeah. We're going to make this b. So 2 to b. All right, thinking about how we're going to integrate this, we're going to use u substitution. U will be the natural log of x because that derivative gives you 1 over x. I guess I'll put that right here. It appears that I'm going to have u down here, and all of this will be replaced with du. So du stacked on top of u, that's going to integrate back to the natural log. So the natural log of the absolute value of u, which happened to be another ln x function here, evaluated from 2 to b. Natural log of the absolute value of the natural log of b minus the natural log of 2. which is just a constant. Okay, let's apply the limit now to b to infinity. All right, so the natural log of infinity is just going to be infinity, so I still have the natural log. This is going to be infinity, which will be another infinity, minus the natural log of the absolute value of the natural log of 2. Okay, well, this is just going to be infinity again, so it's going to diverge. Infinity minus this small value right here has no effect on anything, so we're going to say this is equal to infinity, and by the integral test we can see that this series is going to diverge. All right, let's take a look at the multiple choice question number 3. All right, we're told that f is a positive continuous decreasing function such that the series a sub n can be modeled by a function. Okay, the question is, and I know you're looking at it on your paper, it's just a mess here. If the a sub n series converges to some number k, which of the following must be true? Okay, so if the series is going to converge, okay, and all of this is true, positive continuous decreasing, okay, think integral test. Okay, so look at choice D. Okay, if the series converges to some k, then we can say that the integral from 1 to infinity of the function converges. Okay, look at the comparison between D and E. D and E are very close. It's just that on D it says that the integral is going to converge. On E it says that the integral converges to k, but remember what we're told up previously about this test, that it doesn't tell us that the sums are equal, it just tells us that they follow the same kind of behavior. So you don't want to choose E, you want to choose D. I've seen that question come up quite a bit. Okay, and I think on this video we're going to try and do one more note card. It's going to go pretty quick. It's going to be Cliff Note 8, the P-series. So let's look at those problems. So you might want to remind yourself, just kind of look over the conditions that have to be met to be a P-series, and then how to proceed if we do have a P-series, determining if the series is convergent or divergent. All right, example 1. Okay, so this is a P-series. We look at the denominator. The power is 2. And if you have a power that's greater than 1, then we know that the series is going to converge. All right, example 2. Okay, yes, you can do this. You can pull the 5 in front, make it a multiplier. There is a property that allows you to do this with series. Okay, it kind of unclutters the nth term here. Okay, and then it's a better visual that you can see the exponent is a half, and that being less than 1 or equal to 1, it tells us that the series diverges. So just kind of be on the lookout for this. Sometimes I'd like to put an extra constant multiplier in here so that you think that it might not be a P-series, but in fact it is. Okay, and the last example here, okay, is a P-series, rewriting it. I don't know where that infinity keeps going. It's going to be n equals 1 to infinity. Maybe it'll stick here. N to the 2/3. 2/3 being less than or equal to 1, so this one also, this series would diverge. Okay, we're going to cover some more clip notes, but in a different video.